we are at the last block, and in this block, what we'll do is to generalize what we talked about today from a single phase setting and generalize them to three-phase setting. So we'll focus on radio network, but unbalanced three-phase model. So the two topics. One is we'll generalize the disk flow model proposed by Brown-Wood back in 1989 for single-phase network with zero-sum element. We'll take that and try to generalize that to a three-phase model. And then we will propose a corresponding linearized model for the three-phase network. Right? So the way we're going to do the generalization to three-phase is to go through an intermediate step, which is that we start with the disk flow for a single-phase network and reformulate a single-phase model. And we'll see what that reformulation is. Again, all details are in the notes, and we sort of saw a bit of this reformulation, but we'll look at this more closely. And the reformulation is such that the two models, right, the disk flow model and this reformulation, the model are equivalent. Again, equivalent in the sense that we discussed before. There's a one correspondence between the solution sets. But it is more convenient. And then we will generalize this reformulated single-phase model to a three-phase setting. So that's the process. And in fact, what we did previously, I didn't recover. Is from here, you can get to SOCP relaxation. And from the convex problem, you can develop distributed OPF algorithm. And this is the distributed OPF that I sort of hinted earlier at the very beginning of today, but I didn't go into detail. And similarly here, from the generalized three-phase model, you can have SDP relaxation. And we'll see that later on today. And in fact, from this convex problem, you could have a distributed OPF algorithm. And this actually was the algorithm in some of the simulation results that I presented at the beginning of today. So what I'll do now is to go through this process, and that will be block 4. Okay. All right. So let's do that. So let's look at the disk flow model, right? So the starting point is disk flow model. Again, we take the orientation where every line points away from the root of the tree, but 0. And when I say ij, I mean that I'm looking at node j, and I is the unique parent of J. So then the model looks like this. We saw that before. Some over order case. So I'm looking at node J, right, and write down the power balance. So this is the outgoing power from node J to the downstream nodes that equals to the receiving power from I to J. So it's the sending power minus the loss plus the local injection. Okay, and then there's this Vj minus Vk to the real part of Zjk Hermitian. So this is a series impedance. I'm ignoring the superscript S because we ignore shunt elements. So all the impedances and admittances they're all series impedances and admittances. Sjk. Okay, maybe I will do this. It's the same. Minus Zjk square Ljk, and then there's this Vj Ljk Sjk square. So that's the disk flow equation for single phase network. So a reformulation takes the following form, where we have the first equation, the power balance equation remains the same. So this is so this will be in the complex variable. Let me make sure. So yes, that's right. So it's the complex variables. Oh, so that's the fix. Yes, okay. So the reformulation will look like the first equation remains the same. Jk, j to k equals Sij, Zij, Lij plus Sj. The second equation, though, does not take the square magnitude stuff. It's basically the Ohm's law, Zij, Jk, right? So the important difference between these two equivalent models is that phase angle information on the voltage and currents, branch currents, are included in the variable for the reformulator model. Right? And then Sjk is simply Vj, Ijk complex conjugate. So this is simply the definition of branch power in terms of the voltage and the current. And then the Ljk is Ijk squared. And therefore, in this reformulated model, we have variables that are Sj, that are voltage phasor, not the magnitude square. No J, we have complex power, and then we have current phasor and is magnitude square. So these are in, let me just call small n, right? So these are complex variables. Whereas in the branch flow model, so these are Pj, Qj, those are injections, Vj magnitude square of the voltage, and then the, let me write in real. So this will be Pjk, Qjk, and then Ljk, right? So this is in real, these are real variables. So different set of variables satisfy different equations, but it's easy to show, well, it's easy to show these two are equivalent in that sense. So that's a reformulation. Now, when, for single phase, when we generalize to three phase, we want to generalize this set of equations. Now, in this set of equations, these two are linear, so it's relatively easy to think about them. You just then this will be three-dimensional vectors. For example, these were three-dimensional vectors, and ZJK is a 3x3 matrix that we saw earlier yesterday when we talk about three-phase models for the best ingestion model. This is the same thing. So this, let me, okay. The really key issue is how do you what is the right generalization of these two quadratic equations from single phase to three phase? And the key insight really is that the right generalization is to use the outer product. So we're going to define Sjk, which is a 3x3 matrix, to be equal to Vj Ijk complex conjugate. So this is a three-dimensional vector, which is, okay, let me write this down explicitly. So this is Vj, 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 A, B, and C, the column vector. And this is Ijk, 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 A, B, and C, row vector, but also complex conjugate. So So this will be complex conjugate, complex conjugate, complex conjugate. So it's the outer product of the column vector V, Vj, and the row vector ijk complex conjugate. And it is a 3x3 matrix. It is 3x3 positive semi-definite and rank 1 matrix. Okay, and that generalizes this into three-phase setting. And the similar thing here is to define the LJK 3x3 matrix to be IJK complex conjugate. So that's really the key insight in generalizing the model to three-phase. And therefore, the three-phase model for the reformulated model is the following. So the Kj power balance is the diagonal of Sjk, the diagonal of Sij minus the 3x3 matrix Zij times the 3x3 matrix Lij, Ij, so plus the local injection vector. Okay, so this is a three-dimensional vector. Okay, sorry. So no wonder. So this is this. So this is 3x3 matrix. This is 3x3 matrix. This is 3x3 matrix, and therefore this is a 3x3 matrix. So this is 3x3 matrix, and we're taking its diagonal entries and make that into a vector. And therefore, this is a three-dimensional vector, just like this. Similarly, on the other end, you take the diagonals of the 3x3 matrix, make that into a vector, and that's a three-dimensional vector. You sum over all the case. So this is simply power balance. Now, notice that in this power balance, only the diagonal entries of these matrices are involved. This constraint, the power balance constraint, does not constrain the off-diagonal matrices, off-diagonal entries of these matrices. Okay, so those off-diagonal entries of, let's say, Sjk will be determined by the next set of equations. So this will be the sort of direct generalization of the three-phase, single-phase system, right? So this is for all j to k. This is for all j, for all j buses j. And again, this is a three-dimensional vector. This is three-dimensional vector. This is 3x3 matrix. Okay. And then the Sjk, as I mentioned earlier, is the outer product of Vj, which is a column vector, Ijkh row vector, and then the the Ljk is also a rank 1 matrix. Okay, so this is the first model of the three-phase radial network, unbalanced three-phase network. Okay, so one can show that this model, let's say model 1. Okay, so model 1 is equivalent to three-phase burst injection model that we saw yesterday. So in the burst injection model yesterday, there's a single phase equivalent of the three-phase model. And if you write down those set of equations, and you can show that the solution set of these two models are in 1-1 correspondence. And therefore, in this sense, the set of branch flow models in three-phase setting are indeed equivalent, all the models that we talked about. Now, this actually holds for a mesh network. Okay. Now, if we specialize to radial network, okay, then And also the same here. For the single phase model here, it holds for branch network, holds for general network, including cycles, a mesh network. Okay, is that when you specialize to radio network, then indeed you can ignore the phase information and have this flow model, which is very simple. Same here, it holds for three-phase general model. Now, when we but the idea of using this outer product to define the right matrices is important. And when we specialize the radio network, then we get a generalization of the disk flow equations. And it looks like this. So the disk flow equations, so this is for radio network. And we have generalized disk flow. Okay. It looks like this. So it looks, the first equation is the same. You have a diagonal of SJK equals diagonal of Sij, Zij, Lij. So these are 3x3 matrix. You take the diagonal, you get a 3x3 dimensional vector plus Sj, just like before. And then you have a small Vj minus Vk. So this is magnitude square, but 3x3 matrix. Okay, so not the phasor. Is Zjk Sjk Hermitian transpose Sjk Zjk Hermitian transpose. So this corresponds to, if you look, let me finish this first. This is Zjk Ljk Hermitian transpose. This is for every line. Okay, let me first explain, let me comment on this. So this is 3x3 matrix. This is 3x3 matrix. Rank 1 positive semi-definite 3x3 matrix. The product is a 3x3 matrix. This is simply the same matrix but Hermitian transpose, right? So these two are Hermitian transpose of each other. This is 3x3 matrix, 3x3 matrix, 3x3 matrix. So the product of 3x3 matrices, you get a 3x3 matrix. Similarly here. Okay. Now, if you look at the this flow model, let me just copy this. Okay, compare with the this flow model, right? This is this. If this is a scalar, if every quantity is a scalar, then this is simply the sum of the scalar complex number and its complex conjugate. Then you just get 2 times the real part. This, if this is scalar, then Zjk and Zjk complex conjugate is simply this. And therefore, in terms of the syntax, formally, they look almost exactly the same. Of course, here's a 3-dimensional vector, 3-dimensional matrix, 3x3 matrix, and 3x3 matrix, and 3x3 matrix. Okay, that turns out to be the right generalization. And then what about this, right? Well, it turns out the right generalization of this quadratic equation is the requirement that, let me move this, oops, is the requirement that the matrix, this is 3x3 Vj, Sjk, which is 3x3, Sjk Hermitian transpose, and then Ljk. This 6x6 matrix has to be positive and definite and of rank 1. Okay, so this is for every j, k, and then the requirement that that this has, Vj Sjk permission transpose in one. Okay, so this is the generalized gas flow model for three-phase radio network without shunt elements. So this is linear in the variables. So what are the variables? The variables are the 3x3 matrix Sjk, the 3x3 matrix Ljk, the 3x3 matrix voltage magnitude square. And then the injections, which if it's a power flow problem, then this vector is typically given, except for the substation. If it is OPF problem, this can be part of the optimization variables. So these are the variables. In terms of these variables, this is linear. This is linear. This is convex. This is the, again, the only non-convex constraint, right? And therefore, the OPF problem in the three-phase setting is simply you want to, let me write that. Okay, so they can, it's simply, you want to minimize certain function of, let's say it depends only on the injections. It could depend on other variables as well. And over the set of variables, 3x3 matrix, 3x3 three-dimensional vector, the injections, 3x3 matrix, the voltage magnitude square, the current magnitude square, 3x3 matrix, and then Sjk 3x3 matrix. Subject to the constraint, which is some operational constraints, such as the voltage magnitude square lies within a certain bound, 5% or 10% square of the nominal voltage, for example. Right? So operational constraints, which may involve only constraints on the diagonal of the Vj matrix. So the off-diagonal entries are not doesn't correspond to any physical voltages, right? But the diagonal entries of the Vj matrix are the voltage magnitude square at node J for phases A, B, and C. You can have injection bounds on the Sj. Those are part of the operational constraints. You can have other operational constraints depending on your application. And then the second set of constraints are those power flow equations above here. All right, and this is non-convex because of the rank constraint. And therefore, a semi-definite relaxation of this is one that will ignore this rank constraint. That's SDP relaxation. Now, typically, the operational constraints are linear, at least convex, but typically linear, depending on your application. Now, for the voltage limits and also the capacity constraints, they are linear. This constraint is convex, and it's kind of subtle, but the fact that it is radial, but three-phase, means that the sort of the single-phase equivalent, sort of, the graph is caudal, where the only click are subgraph of your single-phase equivalent. The clicks are the subgraph corresponding to each line. And therefore, this PSD requirement is imposed only on those subgraphs. But since these are the only clicks, then what we said yesterday about these caudal extensions and caudal PSD or partial matrix PSDs and partial matrix Rem1 and stuff, it means that the fact that we are imposing only PSD constraints only on sort of the partial matrices for every line is sufficient to make sure the entire matrix for the entire network is PSD or is completable. There's a completion to the whole matrix that is PSD. Right, it's some subtle thing going on, but it's not important. The important thing is that it turns out this very simple PSD constraint on only 6x6 matrices is sufficient to guarantee the whole problem when it is exact will give you a global solution for the original non-convex OPF. Okay, we don't need to look at PSD conditions on a bigger matrix. That's the key. And this really also underlies the distributed algorithm that I don't have time to talk about. It turns out that you can just solve very small, regardless of the network size. That's the key. Regardless of how big the network is, you just need to solve eigenvalue problems of 6x6 matrices in order to get this distributed OPF that runs very, very fast. And that property, this nice scalability property, boils down to this this caudal structure of the network, and then the properties of partial matrices and stuff. That's what gives you the nice scalability property, where the sub-problem you have to solve during your computation doesn't scale as your network size increases. Okay, so that's just some mathematical structure on this thing. Okay, so that's all there is to say about the OPF in three-phase this generalized disk flow model. You get this set of equations. The only constraint that is non-convex, Rem1, that's what makes your OPF non-convex. And if you ignore the Rem1 constraint, you get an SDP relaxation. It's not SOCP. And the reason it's not SOCP is because this is more than quadratic inequalities. So if you write this down, it can be degree 6. Okay? So it is higher order than second order, but still much smaller than, let's say, the size of the network, right? So instead of n or n plus 1, you get a 6th order polynomials to solve. That's much simpler SDP relaxation than a full SDP. Okay, so that's the relaxation. Let me see. Okay. Oops. Still run out of time. Okay. Let me just then quickly explain what the linearized model is, so I can ignore this. So the linearized model. Let's see. So the key assumption is one that similar to the linearized model for single phase model, that we can ignore, we can set this to 0. So what it means is that the line loss, which is ZJK, LJK, small. Oops. Compare with SJK. Okay. Secondly, which is the key assumption for three-phase, is that reasonable? Seems okay, but it is an approximation. And the approximation is that essentially the voltage are balanced, which means that for every node, if you look at Vj in phase A and B, they are separated by 120 degrees. Say VJB, VJC, and VJC, VJA. So they are 2 pi over 3, 120. So it's balanced voltage. So the magnitudes are the same, angles are separated by 120 degrees. Now, what is the implication of these two assumptions on the linearized model? Well, we look back at this thing. We can ignore L, just like what we did for the single phase. And we can ignore this, right? This is like the quadratic equality in a single phase case. So the single phase linearized model will have something like this. Well, this, but without this, okay? Now, if you look at this, if you just ignore L, with the first assumption, you can ignore L already. But this does not constrain the off-diagonal entries of SJK. It only constrains the diagonal entries. The second assumption, the fact that the voltages are balanced, allow us to compute the off-diagonal entries of SJK from its diagonal entries. That's the purpose of the second assumption. So let me maybe elaborate on that a little bit. So because of this assumption, we can write Vj. Vj's three-dimensional vector is determined really by a scalar. Let's say Vj of A, right? So this is a scalar that determines the entire vector, because phase B, phase C will just be this, where alpha is e to the minus j. J here is the square root minus 1, 2 pi over 3, right? So it's just 120 degrees. So we get a three-dimensional vector, but determined only by a single scalar. What this means is that we can determine the off-diagonal entries of SJK from its diagonal entries only, as follows. So the key thing is to look at the this expression, which defines a branch power flow, and this is we substitute Vj, right, to be determined by Va only. So you get the scalar Vj, and then this is 1 alpha alpha square, and then you get ijk A, B, C complex conjugate. So what does this mean? It means that the columns of SJK, so there are 3 columns, each column is in the span of this. So let me call this beta vector. So the columns of SJK are in the span of beta. So they are multiples, complex multiples of the beta vector, right? And so if you look closely, let's say at the first column, okay? So the first column will be 1 alpha alpha square. This multiplied by this, that will give you the first column, right? Times Vj A ijk A complex conjugate. So this is a scalar. This is 3-dimensional vector, and that gives you the first column of SJK. Now, if you look at this, this is simply the the first diagonal entry of SJK. That's my point. So, and therefore this becomes 1 alpha alpha square. Let me denote this by lambda JK. So lambda JK is going to be the diagonal, the vector, three-dimensional vector of SJK. Okay, so you take the 3 by 3 matrix, but you only look at the diagonal entries, which you can determine from this equation without the L. So once you have the SJK on the diagonals, then you can figure out the off diagonal through this. So you take the diagonal entries of SJK, which you have determined, that gives you the vector 3-dimensional vector, and this is the first element. Okay. Similarly, for the other, if you look at the second column, which is this multiplied by this scalar times this, you massage it a little bit, you will conclude that the second column will be of the form, which is alpha square 1 alpha times the second off diagonal entry. And similarly for the third column. So putting all this together, you will get from this relationship the following, which is SJK equals to is there lambda? Okay, gamma. So what is gamma? Okay, equals to a 3 by 3 matrix gamma, which I'm going to write down, times the times the lambda JK, which is 3. So so lambda is a matrix. Okay, sorry. So so let me explain what this is. This is a three-dimensional vector, lambda JK 1, 2, 3. You make that into a diagonal matrix. So this is a 3 by 3 matrix with lambda JK 1, lambda JK 3. Okay, this is a three-dimensional matrix that is a constant. So it's just this. Right, which are these things, put them in the right column. This will give you a three-dimensional entire matrix SJK. So the point again is that you get this from the power balance equation. You get the off diagonal entries of, so this will be the diagonal entries of SJK, and the off diagonal entries of SJK is this diagonal matrix multiplied by this constant matrix. So the upshot of all this is the linearized model for three-phase generalized distal model is the following. So this is a linearized model. Power balance. So this is not, sorry. So this is just three-dimensional lambda ij plus sj. So these are all three-dimensional vectors, right? And we know that the lambdas are going to be diagonal entries of the Sij or Sjk matrices. And Sjk is the gamma matrix, which is a constant matrix, and the diagonal matrix constructed from lambda jk vector. And then you have Vj minus Vk, Jk, Jk, Sjk, Cjk. Okay. So this is three-dimensional, 3 by 3 matrix, 3 by 3 matrix obtained from here. this is simply the Hermitian transpose of this matrix. The sum of these two, you get a real matrix because it's a sum of complex conjugates. And that matrix is the difference matrix of Vj and Vk. Okay, so I'll stop here. This is the linearized model, and you can also write down explicit solutions just like in the single phase. Almost all the nice properties of the linearized model for single phase, many of them will generalize to the three-phase case. Okay, sorry, I'm running as usual longer than I hoped. So we have a few minutes. So maybe if there are some questions that I should answer for day 2, I can do it now. And then I will try to answer some of the questions for day 1 on campus. So Arthur, do you have questions that I should answer?
You have 3 questions on the Q&A. I think it's better if you read them, like you just
let
there.
Me
on the
let
bottom.
me the model in network, how do we define a cycle? Is a cycle defined inside? Okay, good. Yes, the answer is yes. The cycle will be defined as a cycle on the underlying underrated graph. Yes. Okay, good. Does anyone know if Australian distributors are using dynamic CVR? Actually, I don't know. I don't know if Luigi or anyone else knows whether Australian distributors or Australian utility companies, I guess, whether they use CVR. I do not know. Does distributed OPF relate to that? Good. Yes, indeed. Okay, so this anonymous attendee, his point exactly right. So the question is, does the distributed OPF relate to the application of dual decomposition of ADMM decomposition for OPF problem? The answer is yes, indeed. So okay, so let me talk about this. There's a single phase version of this, and then there's a 3-phase version of this. The ADMM algorithm, for those you know, is an iterative algorithm. Within each iteration, you may have to solve a optimization problem. And you can solve the optimization problem also iteratively. So there's an outer iteration and there's an inner iteration for every outer iteration. But because of the quadratic structure of in a single phase case, because of the quadratic structure of your powerful equations, you can actually okay. So before we get to that, indeed, how do you use the dual decomposition for ADMM, but also you employ the sort of a somewhat standard trick where each bus, right? Suppose the control agent is associated with each bus. It could be more general than a few buses that are controlled by the same agent, and you have a few agents that communicate. That's fine. But in the extreme case, think of each bus has a control, and you want to have a control that make local decisions based on maybe information from the neighbors. So what do? Well, you need to know the state of your neighbors. So what you do is that you have an estimate of your neighbor's state. That is the local information. Based on those estimates and your own state information, then you can make local decisions. So that's the first step you have to do. You decompose them. Now you impose a constraint at the end where there's a consensus constraint where the local estimates of everyone else's state must be equal to the true state when things converge. So that's a consensus constraint. So you have local copies of state, and then you have a consensus constraint that decompose the problem into a distributed version. And then you do this ADMM. Then you if you decompose them, the first step in the right way, then for single phase, you can actually explicitly solve the solution, the optimal solution of your subproblems. So that in each outer iteration, you don't have to solve your sub-optimization problem iteratively, but you can just write down the explicit solution. That's what speed up the entire ADMN dramatically. Is many hundreds of orders of magnitude faster in a single phase. In the three-phase case, what happens is that you don't have quadratic equations that you can solve explicitly. Well, you have so if you decompose in the right way, in each outer iteration, you have to solve a whole bunch of subproblems. Some of those subproblems are still quadratic equations that you can solve. Some of the subproblems will become eigenvalue problems that you have to solve. It's not an explicit solution. But those eigenvalue problems, as I mentioned earlier, does not depend on the size of the network. That's the key. It's only 6 by 6 matrices. So you solve those eigenvalue problems very, very fast. It's just linear algebra in each outer iteration. And again, which means that every outer iteration is orders of magnitude faster than if you do the normal thing where you solve each sub-optimization problem iteratively. So that's you put all these things together, you get this nice distributed OPF problem based on ADMM for three-phase model that's very fast. Okay, long answer, sorry. How to solve a large-scale mixed integer SDP? Unfortunately, I don't really have any good comments on this one. When you have mixed integer problem, it's computationally generally much, much harder. There are all kinds of techniques people have developed. You can do branch and bound. You can relax it to integral constraints and many other things. There's no general magic bullet that works for all problems. You just have to look at your particular problem, try to exploit any structure that you can exploit and try different techniques to see if at least one of them works. It is tough whenever you have integer constraints, integer variables. Can you please good reference for this? Okay, so there's quite a bit of literature on distributed OPF. So I don't have one single good reference. There are many, quite a bit of literature. Yeah. Since the linearized power flow models is over approximation of the actual nonlinear power flow, how to quantify approximation error in solving using solver? This is the second, where's the control computer by? So it's an approximation, and therefore the control computed by lin disk flow. Oh, I see. So maybe you are referring to this mobile control using the linear disk flow model. It doesn't guarantee actual nonlinear solver. So I'm not exactly sure what you mean by guarantee actual nonlinear solver. But it is an approximation. If you okay, so maybe here's the interesting problem that relates to what you're asking, I think. Suppose the reality, which is the real network, of course, is extremely complicated, can be approximated well by the nonlinear disk flow model. And therefore, and then you use linearized disk flow to approximate that. And therefore, for the linearized disk flow, the reality is simply AC disk flow, right? Nonlinear disk flow. Then you can ask a question to say, suppose you apply the control that you compute using the linear model, right? Just like what we went over. Apply the control to the real network, which is the nonlinear disk flow. And therefore, when you apply the Q, the nonlinear disk flow is going to produce an actual V. And then you iterate. You said, okay, so this is an interesting question. So this is the nonlinear disk flow, which is for us, the reality, okay? Which will produce a V as a function of the Q so this is V of T, okay? Now, the linear disk flow is the model that you use in order to figure out your Q. So your Q of T is some control, it's all localized, but in the vector U of your V Q of T minus V ref, okay? So suppose, now the important thing here is that this V is not the V produced by your Sorry. So let me use this. This is V hat. This is not the voltage, the actual voltage. So this is QT. This is the V of T. Okay. So okay. Sorry. Yeah. What I mean. So this V is not the voltage from your linear disk flow model, but is the actual voltage produced by your nonlinear disk flow, but you measure it, okay? But the design of the yield depends on the linear disk flow. So the design of flow uses the linearized model, but once you have designed the control, you can just apply it to the nonlinear reality, which is this, right? And then you can ask, and therefore, to your question, then the relationship between the different variables in the linear model and nonlinear model is exactly this. One is the approximation of the other. That's all we know. But you can ask if you do this, right, which is very close to what you actually can do in reality. Will this closed loop system be stable? Will it converge to equilibrium point? Does the equilibrium point possess some nice properties? For example, it optimizes some metric, for example. You can still ask the same set of questions, but it becomes much harder. What I went through this earlier today is to replace this box, right, by a linear disk flow. So if this is a linear disk flow where this function is simple, it's affine, then we can analyze the closed loop system, we can prove convergence and optimality. If this is replaced by the nonlinear function, it's much more difficult, but it will be an interesting question. So what time is it? Okay, so it's 4 minutes over. If there are not that many questions, what I can do is that whoever needs to leave, please feel free to leave. But there's only a few questions left, so I might as well just go through them. Is there any way for solving infeasibility problem in SOCP? Oh, there are many heuristic ways to, infeasibility problem in SOCP. Okay, if I understand your question, then if it's asking if SOCP is infeasible, then there's not much you can do. Then you can't even solve the relaxation. If the original OPF is, well, first of all, if SOCP is infeasible, then we know that the original problem is infeasible, right? This one is a superset. In terms of feasible set, it's a superset. If the original problem is infeasible, but SOCP is feasible, then you will get a solution that is not very useful because your original problem is not feasible. There's not much you can do. Well, there are many things you have to do in practice. Mathematically, there's not much you can do if the original OPF is infeasible, even if your SOCP is feasible. So I'm not sure. Answer your question. Can you why we check it? Oh, so okay, good. Now in the disk flow, okay, model, you get a solution which is some real vector, right? So it's the VJs, SJs, SJKs, and LJKs. Okay, so these are real in some M. Okay, there's no voltage angle or current angle.
Professor Steven, can you hear me? Because we cannot hear you. Professor?
Solution. Okay, let me turn on my Wi-Fi and try to switch. Hello?
Hello, now I can hear you again. We saw your drawing, but we couldn't listen to you.
Okay. All right. So so when the Wi-Fi is on, I will switch over to the Wi-Fi connection. on the other hand, I'm not sure when we switch over, it might cause everyone to drop.
No, actually, now I think it's okay. You
It's
can
okay. All right, let's continue with this. So I'm not sure where the connection was lost. So I'm looking at the question that why do we need to check cycle condition, right? So in this flow model, there's no angle information. So this is the variable we can solve from this flow model. There's voltage magnitude and current magnitude, but no phase angle. We must be able to recover from X, the powerful solution of this flow. We must be able to recover from X, the voltage and current angle information. If we cannot, it means that the X solution we get is not a valid solution. So why can we get invalid solutions? The answer is that, remember, one of the equations is something like Vj Ljk equals Sjk, okay? So when you take the square of equations, you may introduce spurious roots. That's the issue, right? Because the original thing is actually the phasor complex conjugate equals this, right? And then there's also this equation, this flow comes from massaging this equation and then taking the magnitude square. When we take the magnitude square, we get, for mesh network, we could get a spurious solutions of your nonlinear these four equations, where you cannot recover angle information. That's the issue. If the X that you get from your nonlinear solution indeed satisfies cycle condition, then it guarantees that you get the right solution, and you can recover the angle. Now, if the network is a tree, the cycle condition is automatically satisfied for every X that is the solution of this flow. That's not the case if you have a mesh network. You can have multiple solutions with this flow. Right? So that's the reason. PMO is better option than MATLAB. Maybe. I don't have any comment on that one.
Professor, we cannot hear you again.
So the question is that whether the example is related to strong duality.
Okay, now you're back. You're back.
Hello? Yeah, sorry. Okay, since there are only a few more questions, maybe let's struggle through this. Okay.
Yes,
so
yes.
Yeah.
Go ahead.
Again,
now it's better. Yeah.
Okay. All right. So is the exactness property related to strong duality? In a way, it is, in the following sense. We have a non-convex constraint problem. You can look at its dual. You can always write down its dual. In general, if it is non-convex, there will be a duality gap. When there isn't a duality gap, then typically it also means that the solution you get is exact in our sense. You can recover an optimal solution of your OPF, a non-convex OPF. So in that sense, it is related. The notes of chapter 13, OPF semi-W yesterday, of course, is not. Oh, chapter 13. Okay, I will take a look and maybe let me take a look quickly right now since I have it open. Okay, wait. So the module. Oh, Oh, okay. So you are okay. I see. So you're referring to the exactness, right? So on Canvas, I have I attach a paper that talks about is a tutorial on semi-definite realizations of OPF, and particularly is part 2 of that tutorial. And part 2 looks at particularly the exactness issue. So that's what's on Canvas. I do have lecture notes on this, but the lecture notes are not in a state that that's readable. So I don't really have notes that I can put on the lecture notes that I can put on Canvas. But that tutorial and also the recent book survey by Dan Mosen and Ian Hisken, that book is also contains a lot of references as well. It's an excellent survey. Linearization of power flow around zero low voltage profile in branch injection model on this one is accurate. And does the linearized power flow model is always accurate? Okay, so zero low voltage profile. I'm not, in the bus injection model, so, but the branch injection model. So I'm not quite understand the first question. The second question is the free phase unbalanced system always accurate? It may not, right? So it's an approximation. So accurate is a continuum term, right? So how accurate? It's an approximation. And what we understand is that where is the approximation, right? The approximation is we ignore the loss, the line loss in the linearized model. And therefore, the approximation is reasonable if the line loss is small. Now, how small is small? Well, compare with the line power on that line. If the line loss is small compared with the line power, then we expect the approximation to be accurate, to be reasonable, right? So that, yep, that's all. Okay, good. Well, thank you all very much. Thanks for attending and also for the questions. Let me see, there was a raised hand earlier, but maybe that's gone. Okay, so that's gone. Good, so I will try to answer some of the questions, yesterday's questions on Canvas. All right, that's it. Well, thank you all very much, and please enjoy the rest of the course on Wednesday, Thursday, and Friday, same time. There'll be 3 other professors from the University of Melbourne. They will talk about different aspects of distribution systems, both the theory and also the applications in reality. So that's very important. Okay, thank you, enjoy, and bye-bye.